Welcome all of you for this class. In the last previous classes, we discussed at stretch lot of things, right from fundamentals of NMR, right from internal interaction parameters. We understood what is chemical shift, we understood what is a coupling constant, and then using the coupling constant, when one spin is coupled to n number of other spins, we understood what is the multiplicity pattern, and there we understood also the nomenclature of the multiplicity pattern, like doublet, triplet, quartet, varieties of things we understood. And we understood what happens for a different nuclei, how the multiplicity comes. Taking for example the carbon 13, which is 1% abundant, how we can get the carbon 13 spectrum for a molecule containing n number of different chemically inequivalent carbons, and how to interpret the carbon 13 spectrum, how to interpret the spectrum of proton in addition to other heteronuclei. What happens when one proton in the proton spectrum, if protons are coupled to not only proton, some other heteronuclei, how the coupling comes. If there are two other heteronuclei coupled to proton, why we do not see the heteronuclear coupling passive spins, that also we understood. And if we analyze the spectrum of many interesting molecules, for example we took the spectrum of carbon 13, carbon 13 are coupled to fluorine, we understood, carbon 13 coupled to proton and fluorine simultaneously, also we understood. And in the heteronuclear examples, phosphorus coupled to proton and phosphorus proton coupled to phosphorus and fluorine we observed. We also saw proton coupled to boron, boron 10, boron 11, mercury coupled to carbon and boron, carbon and proton, and many such examples. I even discussed about the tetramethylsilane, how tetramethylsilane spectrum will come. All those examples we understood. So that was only to train you how to analyze the spectrum right from fundamentals of NMR, which I discussed. Now you have come to the level of analyzing the spectrum of any given nuclei. All you require is the chemical shift information. All you require is also the coupling information. Some information about the molecule of your interest, nuclei which is coupled to that, its abundance, its presence, how far they are situated, the coupling strength depending upon one bond, through bond, etc. All this information if you have in your hand, or if you are familiar with that, mind it, with the spectra are very simple. If they are called first order spectrum, which I tell you what are the first order spectrum when you go out further, they are very easy to analyze. All you need is little practice. Okay. So that is why I brought you up to the level of making you to analyze the spectrum. Now today what we are going to discuss is some mathematical tool. I do not want to scare all of you with mathematics, because without mathematics there is no NMR. You require mathematics for NMR, that is necessary. But in all the classes, especially in the previous course, I did not touch upon any mathematics. I avoided everything because it was mentioned that course was only for the chemists. I did not want to frighten them. So I used only as much as possible conceptual understanding without going into the deeper mathematics. No quantum mechanics was discussed, no Fourier transformation, no product operators, nothing was discussed. But remember, in the very first class I told you, you apply radio frequency pulse, collect the NMR signal, you are going to collect the signal in time domain. Instantaneously you create a phase coherence, and then there is a decoherence taking place. Simultaneously the signal will go back. While going back, it will induce the EMF in the receiver coil, and then that EMF we are going to collect as a function of time. We digitize the data, collect the signal, and then the time domain signal can be converted to frequency domain by a mathematical operation called Fourier transformation. This is what I said, and I gave you an equation, but we did not discuss anything more. Remember, Fourier transformation is one of the important concepts. It is required in NMR. So we should understand something about Fourier transformation. Many of the concepts of Fourier transformation, many of the laws of Fourier transformation, you are using every day. In your daily life, when you are taking NMR spectrum and analyzing, without your knowledge you will be using it. And we will try to get the idea, because this being a little advanced course, I want to give you some brief information about the Fourier transformation, the laws of Fourier transformation, Fourier series, etc. But in this case, a mathematics is more involved in this. Remember, I could not make the PowerPoint of all these mathematical equations, that it involves too much. So I have written equations by my hand, solve the equations, integrals, everything by my hand. So as a consequence, If you have any readability issues, we can discuss, nothing to worry, but I hope you bear with my handwriting. We will start with the Fourier transformation right now. Okay. The Fourier transformation, we will start first with a wave motion. If you consider any wave motion and a motion along a circular path, we can always discuss or describe this by two functions. It is two trigonometrical functions. One is a sine function, other is a cosine function. These are the two functions. If we have, we can define this wave motion and motion of any particle or anything on in a circular path. For example, this is a function which is a cosine function, because you know at 0 origin this value is 1, as you know cos 0 is 1, and there is a phase difference of 90 degree between cosine function and sine function. That is why sine function starts with an origin it is 0, there is a phase difference of 90 degrees, and this is a function which can be described by an equation. A is cosine of omega t, A is the amplitude and omega is the frequency as a function of time. This is sin omega t. That is all the way we have to represent a wave motion in cosine and sines. Only difference between these two is a phase difference of 90 degrees. That is all you remember. And remember, as a function at the different intervals of pi by 2, it is marked. At cos 0 is 1, and then at cos pi by 2 it is 0, cos 90 is 0, and then similarly sin 0 is 0, of course sin pi by 2 is 1, like that. It is a very easy to phase shift of 90 degree to plot this graph. So, but what happens if I take one full cycle? From here to here I consider one cycle. From here to here I consider one cycle. One cycle means 0 to 2 pi or minus pi to 2 pi, whatever you want to take. And if I take this function and integrate over the volume, integrate over this region, entire region 0 to 2 pi, what is going to happen? Remember this, if I take this area, this and this get nullified. Similarly, this and this get nullified. So, integral of these two functions over one period 0 to 2 pi or minus pi to pi is 0. This is a point we should remember. Okay. Now, we will go to a circular path, motion in a circular path. It is described by sine function and cosine function again. Of course, x component is again a cosine function, x component of it is given by x of, it is resolved. This is, let us say, the object which is, let us say, undergoing circular motion, and this hypotenuse is called r of t, I am going to call it. It can be expressed by an exponential function e to the power of I omega t. This can be resolved into cosine and sine functions, and x component of this is cosine omega t, and y component is a sine omega t, and omega is the frequency, it is given by 2 pi nu, circular frequency. Okay. So, this is a wave motion along a circular path. So, what I am trying to say is, in the previous case wave motion and also along the circular path, all these things we can simply represent by trigonometrical functions of cosines and cosine. These two functions are enough to describe motion of all these things. Now, let us consider another example. You would have heard of sounds produced by musical instrument like tabla, veena or something. It contains harmonics, but its time variation always do not appear as a sine or a cosine. It does not have a sine wave pattern or a cosine wave pattern, but it has harmonics, keeps repeating at different intervals, no problem, but it does not follow sine wave or a cosine wave. But the waveform is periodic, as I said, it repeats at regular intervals. What is the repetition frequency? There is a base frequency with which it gets repeats at multiple intervals. At the multiple intervals of base frequency, both these functions, not both these functions, both this sound which is produced by any musical instrument gets repeated. That is why it is called periodic. And it can be for any other varying function. It may be true not only for this sound produced by the musical instrument, for any other of the functions, many a time periodically varying function need not be always produced, you can reproduce it by sines and cosine. It is not always possible to represent by sines and cosine, but it may contain harmonics and multiples with the base frequency. So, let us see what are the periodically repeating functions can be represented by sine and cosine, or we will try to understand. One of the things you can see is a square wave. Is it periodic? Of course, yes. This is the base function, with some interval keeps on repeating n number of times. It is a periodically repeating function. It is a square wave. Now consider this one. It is a sawtooth wave. again keeps on repeating n number of times. It is also periodic function. Take this is output of a half wave rectifier. You know that in electrical, you can, in electronics you would have studied, you have a half wave rectifier, you have a function here 0 function it repeats. It is again a periodic function. This is a output of a half wave rectifier. This is also periodic. So, all this can be represented by what is called series of sines and cosines, which consists of multiples of a base frequency. That is a point you should remember. They are periodic functions, but they are represented by the multiples of a base frequency. So, then such type of series which you can represent this periodic function as sines and cosines with a base frequency is called Fourier series. Remember, I am not talking about Fourier transformation. I am introducing only Fourier series. Fourier series are the representation of the periodic functions as sines and cosine with multiples of a base frequency. That is all is the definition I am giving you broadly for Fourier series. Now, I want to give you one difference between a power series and a Fourier series. Of course, power series are also there, which can also be used to represent periodic functions. It is possible. For example, this is a power series. For a given periodic function, one can generate a power series to represent that. It need not be sines and cosines. It need not be trigonometric functions. You can have a power series like this. Now, the question is, these coefficients in this power series, how do you determine, like A0, A1, A2, A3, these are all the coefficients of this power series. It keeps going, series continues. It is 0 to infinity is there. Of course, we have some limiting values later, that I am not going into the details of mathematics, but there are coefficients A0, A1, A2, A3, etc. We have to determine these coefficients of this series, power series. How do you determine that? Normally, it is done by successive differentiation. You have to differentiate one, further differentiation like that. Successive differentiation you have to do to get these coefficients. Now, the question is, what happens if the function is not continuous? If it is not continuous, if there is a breaks or if there are terms, you cannot differentiate. One of the conditions of differentiate function for being differentiable, it must be continuous. If it is not continuous, sometimes you cannot differentiate. That is the one problem you see in the power series. That is why Fourier series is a very useful thing which we can always use. And there is an advantage for that. It can represent discontinuous functions also. For example, in the we saw there are several functions with periodically coming. There could be discontinuous, no problem. And it can represent the functions that have corners like this. So, advantage is there for the Fourier series, but there is some difficulty. Fourier series compared to power series will not converge as rapidly as the power series. You would have understood, I do not want to go into the much basics of mathematics. You can find out whether the series is converging or diverging. If you want to converge this thing, see the Fourier series, if you want to converge it, it does not converge as fast, as rapidly as the power series. The Fourier series do not converge rapidly. This is one difficulty. But of course, the advantage is it can represent discontinuous functions and functions that have corners. Now, this is a simple Fourier series. It is simply an expansion of representation of terms in sines and cosine. I am giving a function f of x. It is given by a series. Of course, a coefficient is a0 by 2, some number, and then it can be represented by series of cosines and sines, and each of them have coefficients a n and b n. Coefficients of the cosine functions are a n, coefficients of the sines functions are b n, and of course, summation is n is equal to 1 to infinity. This is general representation of the Fourier series, where we are expressing the terms in sines and cosines with a0 by 2 as the first term. So, the summation starts from n is equal to 1 to infinity. Now, question you may ask me, I can represent by sines and cosine. What are these coefficients? How do we determine that? Okay. How these coefficients are related to the periodic function? It depends upon the periodic function. If I know the function and its periodicity, I can find out a0, an, bn, etc. All the three series we can find out. So, if I want to find out these coefficients, I should know the periodicity of the function. For example, if I want to find out a n, I will integrate the function from 0 to 2 pi of this function f of x into cos of n x into dx. This is the cosine of n x. I will integrate 0 to 2 pi this function f multiplied by cos n x dx. For the coefficients b n, I multiply this, integrate this function again 0 to 2 pi, this function f x multiplied by sin x dx. Remember, if I multiply by cos x and dx this function and integrate 0 over 0 to 2 pi, I can determine a n coefficients. If I do the same thing by multiplying sin x and dx, integrating over 0 to 2 pi, I am going to get coefficients b of n. Okay, so these are the things which we need to find out. And how do you calculate n? N can take value. What are the values of n? It can take values 0 to 1 to n, any number you can take. So n can take values from several values 0, 1, 2, 3, etc. Okay, these are my, I am sorry about my handwriting, since I cannot write this by equations by PowerPoint, which is too time consuming. I have written by this thing. So very simple is, you should, these are all definite integrals. Why I am giving this thing is, these are the integrals, we do not need to do anything. You do not have to integrate this function. You do not have to go for rigorous mathematics. Very easily, if I consider the function here 0 to 2 pi sin of n x dx, if I take it, of course 1 over 2 pi, if you want you can take it or not, no, does not matter, and it will be 0. This is a well known definite integral. So these are the integrals, for example 1 over pi 0 to 2 pi integral sin mx into cos nx dx, that is also 0. Whereas 0 to 2 pi sin mx into sin nx dx, if you take, that is at different values. For m not equal to 0, if sin mx is present, this function is 0. Whereas sin m equal to n, both are equal to 0, both are not equal to 0, this is equal to 1. Whereas for m is equal to n, both equal to 0, sorry, this function becomes 0. So these are some useful definite integrals. Similarly, this is for sine function. What about for the cosine functions? Do the same thing. 0 to 2 pi cos mx sin n, cos nx dx, if you take, same way for m not equal to 0 it is 0, for m equal to n not equal to 0 it is 1, but only difference is for m equal to n equal to 0, unless for this sine function which is equal to 0, here its value is 2. These are all well known in the book of integrations. Go to any book on integral calculus, this is very easily available. You can see it is, you do not have to think too much, you do not have to work out anything. You have to remember this. I am giving this to you because I am going to use this very often in future in this class. Okay. Now the question I asked you is, how do you determine a n, b n, a 0, etc. How do we do that? For getting a n, simply what we have to do with the function, I told you already, multiply by cosine of x and integrate from 0 to 2 pi. In the previous 2 slides I showed you that. For getting b n, I said multiply by sin x, sin n x and integrate from 0 to 2 pi. That is what I said. So now we will do that. 0 to 2 pi, I will take it, take this function f x, multiply cos n x and dx. And this I can express as a series. F of x, you know, is a series which can be written 1 over 2 pi is a naught by 2. Of course, in the earlier I showed you the sequence, you can write it as sine and cosine, that is a series, Fourier series. It is a naught by 2 cos of n x and the integral of a1 cos n cos x, and I multiply by cos n x. Remember, if you want I will go back and show you the this thing here. See, this is what I am using. See, the a naught by 2, this equation I am using, and I am multiplying by this cos of n x and integrating. That is all I am doing here. Okay. Oh, this I cannot erase it. Okay. So this is what I am now trying to do here. I have taken this function, the Fourier series, I have put it, multiply cos of n x each term, both for a1, b1 coefficients are present, and this is a cosine term, this is a sine term, multiply this and then expand it as a series. That is what I am trying to do. As I said, for finding the bn, we have to multiply by sin x, and sin nx. For multiplying, for finding an, you have to multiply by cos nx. This is what the thing which I explained. This is called an. For obtaining bn, of course, same thing you can do, multiply by sin of mx. So same thing, 1 over 2 pi integral series you can continue, and then if you solve it, you are going to get bn. Now question is, you get an and bn, fine. Here also you got an here by putting multiplying by cos of nx and integrating over, expanding this function and integrating over the region. Now same thing I do for bn, multiply sin mx, fine, I can get bn. What about a0? a0 is something different. There was no cosine or sine function here, if you remember that function a0, we multiply by sin cos of nx here to show, but actually it is only a0 by 2. So now how do you get a0? For getting a0, you have to integrate the function of f of x for one period. What is one period? I showed you it is 0 to 2 pi. 0 to 2 pi of this function f of x, if you take, I can integrate and then get value of a0. It is very easily it is done. F of x is expanded here, 0 to 2 pi a0 by 2. Again same simple mathematics is done. I have expanded this function f of x into a1 cos x dx, a1 cos 2x, sin nx, sin 2x, like that, keep on writing series. So a's and b's are present here. I have expanded this integral, that f(x) function. Only thing is now I am integrating over 0 to 2 pi here, this a0 by 2. Okay, this function is integrated by here 0 to 2 pi, and then we can expand like this, except for the first term which become a0, all other terms are 0. Why they are 0? Remember, I gave you few definite integrals as a sort of a table or a chart for you to use it. I just use those things, that is all. I did not do explicitly work out integrals. You can do that, it is not difficult at all. Simply I have expanded this and integrated from 0 to 2 pi, but I know after doing this all these terms will go to 0 except a0. And see, for example, I will take how to work it out, how to get the a0. It is only theoretically I was explaining to you. Can we do it for a real function? Can you work out this Fourier series? Take an example of a square wave. This is a square wave we discussed here, and remember it starts with 0 here. How do you define this function now? It has a function which has a value from minus pi to 0, it is 0, and 0 to pi it is 1. You can define this function. Looking at this function, you can say that minus pi to 0, this function is 0, because minus pi less than 0, this value is 0. For 1 is equal 1, for 0 less than x less than pi. So this is 1. So this is the way we define the function. Now I can calculate a0. How do I do that? As I told you, a0 is integral of 1 over pi into minus pi to 2 plus pi fx dx. Of course, minus pi to plus pi, 0 to 2 pi both are same. It is one cycle. Finally, I am trying to tell you we have to integrate over one cycle to get this value. Okay. So this is what it was. It came earlier itself. So now it is this is resolved into two terms. How? Minus pi to plus pi. I wrote from minus pi to 0 fx dx and 0 to plus pi fx dx. I just resolved into two terms. Minus pi to 0 is what? Fx 0. That means this term is 0. For 0 to plus pi, what is the fx? Is 1. So this integral turns out to be a0 is equal to 1 over pi into pi minus 0. Now I am putting the limit, limit is 0 to pi. When you put that, this turns out to be 1. For a square function, square series, for the Fourier series of this square wave, a0 is 1. You understood how we worked out? Very simple. All I did is I integrated this function from minus pi to plus pi over one cycle, resolved into two terms. One term integral goes from minus pi to 0, other term integral goes from 0 to pi, and then because the way we have defined the function from minus pi to 0, this value is 0, fx is 0, and 0 to pi fx is equal to 1, and it is going to be 1 over pi fx dx is equal to just x. So it is 1, and you are going to get a x substitute from 0 to pi, you are going to get 1. This is the value you are going to get. So, a 0 we worked out to be 1. For n not equal to 0, what happens? A n I have to calculate. A n and b n are the other terms, coefficients which we need to work out. For n not equal to 0, a n can be, I told you, we have to multiply by cosine of n x and dx and then integrate over one cycle, minus pi to plus pi. Now again resolve into two terms, minus pi to 0 f x cos of n x dx, 0 to pi f x cos of n x dx. All I did is simply remember I have multiplied this function by cosine of n x and integrating over one cycle. But again what is this f x? 0 to minus pi to 0. From the limits, from the functions limits which I have shown actually earlier, it is 0. f x is 0 in the range minus pi to 0. Minus pi to 0 in the range f x is 0. What is f x in the range 0 to pi? Plus 1. This we know. So now substitute that, then it is integrated, it is going to become 1 over pi 0 to pi 1 into cos of n x dx. That means this is equal to simple formula you should know, basic integral I am not going to work out, which can be written as 1 over n pi into sin of n x 0 to pi, sin n x 0 to pi. This is the formula. So what I did is I just resolved into two terms. This term I know, this in the range, this term goes to 0 and this term is 1, and I substituted the limits, and this is what we are going to get. So for n not equal to 0, a n equal to 0. So n if not equal to 0, what will happen? Sin 1x. You have to put the values of the limits for pi. You know that. Then what happens for n not equal to 0, a n equal to 0. Okay. So similarly now we can work out b n also. How do you work out b n? Same, b n you have to multiply sin of n x, I told you, and again integrate over one cycle. Now what you are going to do? Resolve into two terms. One term, of course I did not write the other one, minus pi to 0, there is 0, f x is 0. So I have removed that, directly I have removed that term. So I am concentrating only on this term. So this again turns out to be minus of 1 over n pi cos of n x 0 to pi. This is also well known integral, that is why the definite integrals I gave you. Now substitute this, when you substitute this limit 0 to pi, this is the formula you work out. This is minus 1 to the power of n minus 1, because cosine of n, cos 0 and cos pi, cos is an even function, cos 0 is equal to 1, cos pi by 2 is equal to 0, and then you can, what the values, trigonometrical values, you can find out this. When you put this limits, this turns out to be 1 over n pi into minus 1 to the power of n minus 1. So now what will happen? For even n, when n is equal to even, this will become positive. So 1 minus 1, 0, very simple. So for n is equal to positive, bn is 0. I am sorry, n is equal to even, n is equal to bn equal to 0. For n other than this thing, for 2 over n pi for all odd values of n, you take it as, let us say n is equal to 1, then what is going to happen? If n is equal to minus 1, so you find out it turns out to be 2 over n pi. So that means for bn there are two conditions you can think of. For n even, bn is 0. For n odd, it is equal to 2 over n pi, because this minus and this minus get cancelled out, and you are going to get 2 over n pi. So the series all bn, now you can keep on varying for what different values of n, 1, 2, 3, 4, 5. If it is b1, you will know 2 over pi. If it is b2, 2 over 2 pi. Like that you can keep working out all the coefficients. Similarly for an also you can work out a1, a2, a3 for all values of n. But only thing is for 2, for even number here bn is 0. You cannot take, you can take for n equal to 1, 3 etc. For 2, 4, 6 it is 0. So that odd terms will be present, even terms will be absent. So now substitute all these coefficients in the definition of the Fourier series. What is the definition of the Fourier series? This is what I said, a naught by 2, an into cos of nx, bn into sin of nx. Now we know we have worked out the an, we have worked out bn, and we also worked out a0 by 2 by integrating over 0 to pi. One cycle we integrated. And this one we know for n not equal to 0, we have calculated n equal to equal to 0. So, n not equal to 0 means, for example, any value if you take 1, 2, 3, this term is 0. Now, for even n, what will happen? Bn is 0, and for odd n, it is equal to, you worked out n over the previous one, you do not forget that, we got it 2 over n pi. So, we can work it out now. For Bn is 0 for odd even n, and for odd n it is equal to n over 2 pi, we 2 over n pi. Now, using this, substitute this for function f of x, a0 we worked out to be 1, remember a0 we showed it as 1. Now, a0 by 2, this value is half, this coefficient an we worked out, and this we are going to get a series function like this, sine function, and cosine function, of course you know already what is the cosine function, what is going to happen for even and odd. Now, of course we can go to the second example to work out. Before that, I think now the time is up, I will take the second example later, but just I wanted to tell you how we got the Bn, how we got an, and we substitute this function, and it is a series. So, for n not equal to 0 what happens, for n is equal to 0 what happens, simply you substitute in this basic equation and you are going to get this series. This is a Fourier series for a square function which is defined like this, and at this place whose value is 0 from 0 to minus pi, its value is 1 from 0 to pi. This is a function we defined, it is a periodic function. For a periodic square wave, a square function which is defined like this with those limits, and this is the Fourier series. That is how we worked out. We can take few more examples later. Another example of Fourier series, and what happens if there is a exponential functions will be there. Fourier series can be expressed as exponential also. All those things we discuss in the next class. We will continue, and then we will introduce Fourier transformation, and from theorem of Fourier transformation also we discuss. So, just today what I wanted to tell you is, I wanted to introduce to you the Fourier transformation, which is one of the important mathematical tool. You need this for NMR, because you use invariably to convert the time domain signal into the frequency domain, to get the frequencies present in that, to get the spectrum and to analyze the frequencies. And then before introducing the Fourier transformation, I explained to you what is a Fourier series. For taking a periodic function, what is a periodic function I showed you, and for sometimes the function is not periodic, it cannot be, it may be, it is periodic, may not be possible to represent by sines and cosines, it is also possible. So, we finally introduce what is a Fourier series, which is nothing but a function f of x equal to a naught by 2 is summations n is equal to 0 to 1 to infinity cos of mx into cos of mx, a n into cos of nx, plus n is equal to 1 to infinity bn into sin of nx. This is a general form of a Fourier series. We wanted to work out what is the coefficient a0. We showed for a square function what is shown, a0 is equal to 1, and an and bn also we worked out what is a simple integral. You have to multiply, for an you have to multiply by the cosine of nx and then integrate over the one cycle. For bn again you have to multiply by sin of nx and then integrate over one cycle, and then by doing simple integral calculus, for which definite integrals are always available in the book, which I did not work out in detail, we could get what are ans and bns. And finally, substitute all this a0, a and bn in the base equation for the Fourier series f of x, then this is what we are going to get. So, with this I am going to stop today. We will continue with another example and then introduce Fourier transformation and other things later. Thank you very much.